to all. A warm welcome to all in our today's webinar, the last one in our webinar series for this autumn. Please ensure your microphones are muted and also your videos are turned off during the presentation. Feel free to participate actively by writing your questions in the chat or saving them for the Q&A session after the presentation. In the last few webinars, we saw more about the conformality characterization and also about conformality of plasma enhanced ALD or spatial ALD. But in today's webinar, we are going to hear about modeling part of the conformality studies. Before we move into the the presentation, I like to say a few words on our ongoing conformality research competition. So it is for the academics. This conformality research competition. It is only for academics. And with this academic research competition, you can get the PillarHall chips for 50% discount price. And maximum number of chips that is available using this academic campaign is 10. That means 2 boxes. And the deadline for getting this PillarHall chips is January 10, 2024. We opted this date because the deadline for submitting the ALD 2024 abstract is February 15. And one of the criteria for participating in this academic campaign is like you need to submit an abstract for this upcoming ALD conference that is going to happen in Helsinki. And this academic competition is not only restricted to PillarHall chips, but the research based on any high aspect ratio substrates are considered for this competition. Both experimental and modeling studies are eligible for the competition. And in this competition, like first we will make a preliminary list of candidates that will be 8 people, and that is based on the ALD 2024 abstracts. And the winner will be judged during the ALD conference in Helsinki. And the prize will be announced later. Now let's turn our attention to Professor Riikka Puurunen, a distinguished figure in the ALD community. For those who are new to the ALD modeling community, let me provide a short introduction to our esteemed speaker. Professor Riikka Puurunen is a professor at the Department of Chemical and Metallurgical Engineering at Aalto University, Finland. She is the head of Catalysis Group. She was previously associated with the VTT Technical Research Center of Finland, and she was involved in the development of micro electromechanical systems. And she is the inventor of PillarHall lateral high aspect ratio test structures. Her group is mostly focused on modeling the conformality in high aspect ratio structures, and also involved in the applying ALD for the catalysis. Once again, thank you, Professor Riikka Puurunen, for gracing us with your presence. And the stage is now yours. Please.
Today, I'll be talking about recent progress in analysis of the conformality of films by atomic layer deposition. Conformality, the capability of a film to coat a complex 3-dimensional structure with a uniform film, what comes to thickness and hopefully also other properties. Why to study conformality? An obvious reason is that semiconductor devices nowadays, they have a lot of complex three-dimensional structures which need to be covered by thin films. And this three-dimensionality is becoming more and more complex, and also new types of thin films will be needed. So for the initial process development of new films, conformality studies will be needed. Also, when choosing a process for a particular application, for comparing processes and choosing conformality studies are needed. Today, I'll be talking about PillarHall test structures that I developed about 10 years ago, of course, in collaboration with others. And one purpose for developing those at the time was actually to compare different ALD tool vendors and to select a tool. And then also conformality studies can offer very detailed information on the kinetics, so reaction rates in processes. And those are needed, of course, to model processes, to simulate feature scale, reactor scale. Before talking about recent progress, I want to give a brief historical perspective to ALD conformality studies. So here on the top left, you see a micrograph by Suntola, shown by Tuomo Suntola, the Finnish inventor of ALD, at the MRS Fall Meeting 1994 in Boston. To my understanding, this is the first demonstration of conformality by ALD. With the eyes of today, covering this step from, I think, a dielectric to go over a metal, that doesn't seem so special. It's actually a really easy thing to do with ALD, but at those times I've heard this was already almost sensational. With time, the difficulty or the aspect ratios to be coated have been increasing. There's a nice example, quite famous, by Ritala et al. 1999 with aspect ratio of 5:1 trenches coated. Then there is circular holes with aspect ratio 43:1 demonstrated in a paper by Gordon et al., where they also came up with a model that's been used a lot. Then Dendoven et al., so from the Tavernier group in Ghent, came up with a lateral high aspect ratio test structure concept where they were manually assembling a structure. So they were using, I think, aluminium foil to cut a certain shape and then pressing that between silicon wafers and creating this lateral test structure that way. And they were going up to aspect ratios 100:1 with a gap height of, I think, at least 100 micrometers. And then the last example here on the top row is the microscopic lateral high aspect ratio test structures developed by me and co-workers at VTT. So we were following the similar principles as Dendoven et al., but we were doing our structures by MEMS processing techniques, so microelectromechanical systems types of microprocessing techniques, and we were heading up to way higher aspect ratios, so up to 25,000:1 in these first prototypes that were published in 2015. And while I will not be talking in this presentation more about powders, I do want to mention that also porous high surface area materials are actually very demanding to coat conformality-wise. So if you'd calculate what's the aspect ratio in such a structure to coat, this recent example of Gale et al. Has demonstrated coating up to more than 60,001:1 aspect ratio. And also there's an example more than 20 years ago from the Finnish catalysis related research, where catalyst pellets with a length of 4 millimeters and a diameter of 1.3 millimeters were also coated through with ALD. These are, of course, all different types of structures. A review was published in 2019 with Belgian collaborators, Kremers et al. And there we were reviewing the experimental and modeling work for conformality analysis, and we came up with a proposed new term and concept, hole equivalent aspect ratio, EAR. And the purpose of this one is to scale things so that you could compare different studies quantitatively, and the hole equivalent aspect ratio is a number that describes the aspect ratio, how difficult it would be to coat if it was a circular hole. So depending on the types of structures, the calculation can be different, but for these typical trenches, we have had, for example, the Ritala et al. Is a vertical trench, and the Gao et al. Example here, it's like a trench, but it's flipped 90 degrees to be horizontal. So for those cases, just divide the aspect ratio of the structure itself by 2 to get this whole equivalent aspect ratio. And then also a brief historical perspective of kinetic or conformality modeling. So we have been working a lot with this in the past years, but of course we are not the first to do that. And I have here collected some references to literature where similar works have been done. And there are already from about 30 years ago from Estonia, Arik and Simon's paper, and there are many from more from the same group that dealt with analyzing ALD just in a flow reactor and how the adsorption front there develops. And there are many others, as you see here. I won't be going through them in detail, but the fundamental ways to describe ALD haven't really changed. So I took one equation from that first paper mentioned here, Arik and Simon. So that shows the rate of change of surface coverage with time. And it shows the forward reaction rate or adsorption rate, and it shows the reverse adsorption rate. And these equations, they are just the same as are used at the moment. So there's the sticking coefficient, there's the fraction of available surface sites, there's a concentration related term, and there's the area related term or adsorption site density related term. So this is what we basically continue from, and I would refer to that review for a more comprehensive overview of papers on this field. And you saw from that summary of test structures that these microscopic lateral high aspect ratio test structures that we have developed at VTT and nowadays available through Chipmetrics, they have really exposed a new parameter space for analysis, because there the aspect ratios that we have up to 25,000 to 1, they are way higher than anything that has been available before. And when you expose a new space for analysis, you sometimes need to develop also new terminology, and that's something we have also done here. So first of all, to be able to compare different studies, there's a term or a concept called dimensionless distance that's now in use. So it means that the physical distance, denoted here x, but in some other studies z or maybe something else, that divided by the channel height where you are growing. So, and that's then dimensionless because you are dividing distance by height. But that still characterizes the length into the structure. And so as for the saturation profile or thickness profile that we want to observe here, so in these structures, these are so demanding, the aspect ratios are so high. The purpose was that no film will ever grow to the end. That was my purpose when making these structures, which would mean that we can always compare processes. We will always see differences, because then the adsorption front inside the structure will always be seen. And yeah, there are 4 different ways looking at the saturation profile or thickness profile in different ways. So first is, of course, the as measured, here denoted with A. So that's what we really measure when we are analyzing our film, is the physical thickness as function of distance into the structure. So nanometers versus micrometers, for example. And what we can then do to that to make things more comparable is, and this is my favorite way of presenting things because it contains the maximum amount of information, the scaled thickness profile, meaning that the total growth, so the thickness, for example, you divide by the number of cycles. And then the distance into the structure you divide by the channel heights, so you get that the dimensionless distance. This is how I'd prefer to present the saturation profile. Then there are 2 ways to normalize this further. I'll discuss the case D here on the bottom right first. Type 2 normalized. So compared to the scale thickness profile, the total growth has been normalized so that you always have 1 at the entrance to the structure, And also the distance has been normalized so that at the end of the structure you are at 1. This is how many of the older modeling works present the results. And for me, this has been actually difficult to understand because it's covering so much under those normalizations. Another way that is a little bit more understandable in my view is what I call the type 1 normalized saturation profile. So here you have on the horizontal axis the dimensionless distance, so the physical distance divided by the channel height. So that's not normalized, it's scaled. And but then the total growth has been normalized so that you start from 1 at the entrance. When it's presented this way, then you can make the assumption that you are looking at the surface coverage actually, and that helps in some modeling. I'll come back to this Arts et al. Method that uses this exact way of presenting the saturation profile. All right, here are the contents of my presentation. I already gave you an introduction to conformality studies. We'll talk about some modeling fundamentals. And after that, I'll introduce the PillarHall lateral high aspect ratio conformality analysis concept. And then after that, we'll go to the main thing of this presentation, recent progress in experiments and results. I'll present an outlook, and then I've included plenty of extra materials in this slide set for the interested. First, atomic layer deposition. Before we do any modeling, it's important to define what we model. And here is a way to present atomic layer deposition as it's modeled. So ALD is based on repeated self-terminating gas-solid reactions of at least 2 compatible reactants. So here they are denoted reactant A and reactant B, and 3 cycles are shown. The way ALD works is that in gas phase, the molecule is brought to the surface by having some partial pressure on top of the surface. Then that is the reaction is allowed to go to completion. So it's a self-terminating, it's a saturating and irreversible reaction. So that reaction goes to completion, and the mass change is observed in the beginning, and then that also the change stabilizes. And after that, the reactant is removed from the gas phase, either by purge or evacuation. And then the next reactant, let's call it reactant B, is brought in, and then the surface is saturated with that, and the reaction stops. And that's how this is then carried out. 1 cycle, 10 cycles, 100 cycles, 1,000 cycles, as many times as you want. And by the way, this image is available. It's used in a recent chapter on atomic layer deposition, which is in the Kirk-Ottner Encyclopedia of Chemical Technology that I co-authored with Dutch colleagues. And this image is included there, but before we published the chapter, we actually uploaded our new images, which we carefully drafted. We uploaded them in Wikimedia Commons with a Creative Commons license so that anyone can reuse those figures without asking for any kinds of permissions, just by citing the source, citing the authors. So this is one of the images, and there are many more. All right. So when we talk about conformal coating in a high aspect ratio feature, then you first need to transport somehow the molecules inside, and then they react. And depending on how the process parameters are, the growth might take place in various diffusion regimes. The most typical one is free molecular flow with Knudsen diffusion. The gas is not very dense, or compared to the structure where it is, the molecules are not hitting each other in the gas phase, but they are interacting or hitting the walls of the structure. Then you are in Knudsen diffusion regime. Another possibility is the molecular diffusion in continuum flow or viscous flow, where the gas molecules are bouncing into each other in the gas phase. So they are interacting with each other, and the molecule wall interactions can be neglected. Then between these, there is the transition regime where both types of diffusion is taking place. And to know in which regime you are, you should calculate the Knudsen number. It's a dimensionless number, so it shows the ratio of the mean free path to the dimension of the test structure that you have. And if you have much higher than 1, then you are in the free molecular flow regime. If you have much less than 1, you are in continuum, and around 1, you are in the transition regime. And so this dimension of the feature you of course should know, and the mean free path you can calculate. It comes from the kinetic theory of gases. Here is the equation, how you calculate it. I won't go through the details except that there's the temperature, there are the pressures, and then there is something called the collision cross-section, and also the masses of your molecules. And the collision cross-section, it's calculated this way. So it tells that how far apart the molecules, or how close they have to be so that collision takes place. So if the distance between the centers is less than the summed radius of those molecules, then collision takes place, and that's how you can calculate the area. So it's the area of this bigger circle here. I wanted to show this because there's actually incorrect formula rotating in the ALD field, where the collision cross-section is calculated just from the sum of these smaller areas. But this is how the correct calculation is done, and I have here some sources for these as well. So this is a standard concept, nothing specifically related to ALD. All right, let's move on. Yes, then Langmuir adsorption. So the surface reactions are typically modeled through Langmuir adsorption. It has lots of assumptions and simplifications, and they all apply in this case as well. And the typical assumption is that you have a single site reaction. You have your molecule reacting with the surface site adsorbing to it, and adsorption can be reversible as well. So you can have the forward and backward reactions taking place. And here's the reaction rate equation. This specific one is from the paper Järvilehto et al., but you have it, of course, in all papers that are doing modeling, and they might use a little bit different symbols, but the contents really are the same. This is also the one that was shown in one of the earliest papers. So there's the sticking coefficient, there's a term related to partial pressure and the impingement rate on the surface. There is the fraction of unoccupied surface sites, and then there is the adsorption density, or 1 over this would be the size of an adsorption site. And if you allow reversible reactions, then there's forward reaction rate, there's a backward reaction rate, that's then dependent on the surface coverage, but often this one is forgotten about or neglected or not allowed in ALD studies. So only the forward reaction is allowed, meaning that you have irreversible reactions. Reversible reactions are not taken into account because they don't fall into the definition of ALD. To simplify things, this is how it's often done. And there's yet one concept that I wanted to introduce, the Thiele modulus, so the adsorption rate divided by diffusion rate. And often ALD reactions are aggressive, they are fast, and in those cases the adsorption rate is faster than the diffusion rate, and then we are at diffusion, so to say, diffusion limited conditions. And that means that the molecules that are entering the feature, they will quickly be adsorbed, and you will be developing an adsorption front. Another possibility is the reaction limited case, where the reactions are slow and diffusion is faster. And in that case, you are filling the feature with the molecules, and they are then slowly reacting pretty much as a uniform front everywhere. And for clarity, this presentation will talk only about diffusion limited cases where we have this adsorption front that we can investigate. So before reaction occurs, the molecules have to be somehow transported into the high aspect ratio features, and there are at least 3 ways to model these, and these are all different. The modeling that I'll mostly be talking about is based on Fick's law of diffusion. So here the molecules are not treated individually, but rather as a continuous medium. This is the diffusion equation. It's the well-known diffusion equation, and there's an adsorption loss term related to that. And in this case, all the important details are actually in this related to the reactant transport. They are in this effective diffusion coefficient. And these diffusion reaction models based on Fick's law of diffusion, they are applicable at any Knudsen number range. Then there are ballistic transport models where individual particles are tracked or calculated. And for example, Markov chain can be used to model those. These do not allow interactions in the gas phase, and these are only applicable at the Knudsen diffusion regime with Knudsen number way over 100. Then there are still publications made with Monte Carlo models. Here is one example from Bott et al. How the calculations have been made. These are also tracking individual particles, and I have seen works that are done at also low Knudsen numbers, and so these are applicable at any Knudsen number regime. I've seen it being implemented through using different mean-free paths. So very different ways of modeling the reactant transport, but basically the same way of modeling the surface reactions. All right, that was the basics of modeling. Then introduction to the PillarHall lateral high aspect ratio analysis. So I realized that it's very soon 10 years from the first time that this microscopic lateral high aspect ratio structure concept was presented outside VTT. So we've been working a little bit longer than 10 years on this, and it was the 29th of November 2013 that these were presented to University of Helsinki in a joint meeting of the ALD Center of Excellence that we had. And we were then working with the first generation prototypes. This is what I already showed earlier, and this was really the proof of concept of this idea. And there are 2 scientific articles that were produced from that, and the very first is written by Gao et al. And I do want to acknowledge Gao's significant contribution here. So we were together working on the first prototypes, and then also the layout for the second generation was jointly made. So we were then improving both the fabrication flow and the layout. What happened with this second generation was that we actually didn't get out any functional chips. And then for the third generation prototype, the layout was further developed. The fabrication flow was significantly renewed, and that actually did deliver functional chips. And then the layout was still further fine-tuned for the 4th generation. And according to the bookkeeping of the PillarHall.com page, there are already more than 20 scientific articles for this or the related modeling. And there's one core paper that describes how these chips, the 3rd generation chips are, and that's by Jim Ylivaara et al. And it's in Physical Chemistry, Chemical Physics 2020. And this work has been financed by Academy Finland and Tekes or Business Finland. And there was also a little commercialization project within VTT. And then when I got offered a position of professorship at Aalto University, I was very happy that my commercialization partner, Mikko Utriainen, decided to continue with the topic, and he has transformed this concept into a company, Chipmetrics. So these chips are nowadays available for anyone for purchase. And there's also an ALD Stories podcast, episode 14, if you want to learn more about the history here. The conformality analysis concept has really remained the same all through the years. So you just place the chip inside your ALD chamber, you grow the film, and then you can analyze the film. So here's a membrane under which a film has grown. And just by looking at it in a microscope, you see how far the film has grown. And actually there's a scale on top of the membrane, and from this you can read that the film has grown about 130 micrometers deep. This, I think, is a dark field microscope image. That's why it looks a little bit with funny colors. And what you can then also do is you can remove the top membrane by adhesive tape, and then you expose really the surface for analysis and that adsorption front for detailed analysis, and you can then do anything with that as you want. And this is a microscope image. Here are reflectometer line scan examples, and here is an example of a TOF-SIMS analysis of the surface. And still, just to show that the concept makes sense and we understand what happens, here is an comparison of measured saturation profiles or measured thickness profiles and simulated thickness profiles, and the simulations have all been made with the Ylilammi model. And there's a lot of, and this is all for the TMA water process at trimethyl aluminum water process at 300 degrees centigrade. Let's look at, for example, here at the panel D of measurement. So there's 250 cycles and 500 cycles and 1000 cycles, showing how the thickness grows and how the behavior in the high aspect ratio test structure is. If we then had the 500 cycles in different channel heights, so chips with different height of that gap, then if you have a small gap that's fully filled by this 50 nanometer film, and if you have a higher gap, then the film is growing deeper. This is the as measured thickness profile. They all look very different, but then when you take the scaled thickness profile, so you divide the thickness by the number of cycles, and you divide the distance by the channel height, then you see that these are already resembling each other much more. And then if you want to go that normalization way, then you still normalize so that in the beginning the thickness is 1. And just to show the simulated thickness profiles, if we look at the panel D here, you will see that this very nicely reproduces the trends and also the quantitative values that we are seeing in the measured profiles. So this means that we basically understand how these chips work. All right, then to the real contents of the presentation. So recent progress in experiments and results. This is a graph from a paper, Jim Verkama et al., Physical Chemistry, Chemical Physics, where we were doing simulations to understand, for example, how the varying of individual parameters affects the growth. Here you have an example where various things have been varied. For example, increasing the pressure and increasing the time, they both are increasing the exposure of reactants, and you are always growing deeper when you are increasing partial pressure or increasing time. So those are completely logical, and they are understood on the basis of earlier modeling works. If your molecule is heavier, it's growing less deep because the diffusion is slower. So here you see how that molecular mass is affecting. Here the sticking coefficient has been varied. So this is the core kinetic parameter of a process. So when you have a higher sticking coefficient, you have a more step-like thickness profile. And if you are varying temperature, if you increase temperature, you are growing less deep. This is because all these simulations had the same partial pressure. And when you are increasing temperature, then for the same partial pressure, you in fact have a lower volumetric number density of reactant molecules. That's the reason for this trend. But what's really interesting here is this central trend. So that's where we have actually varied the growth per cycle, which can also be seen as adsorption capacity. So a higher adsorption capacity means higher growth per cycle. And we see a very strong trend that a higher adsorption capacity leads to lower penetration depth. It leads to a higher thickness, but lower penetration depth. And this has been varied in a high range, and the trend here is very clear. The 4 per square nanometer is a typical value that corresponds to, for example, roughly the trimethyl aluminum water process. So we see from here, by varying just one parameter at a time, that penetration depth is about inversely proportional to the growth per cycle. And this result is new, and it is something that's maybe not totally intuitive at first, but it is something that has been observed experimentally. So in one of the 2 papers made with those first prototype chips, Mattinen et al., this was a University of Helsinki collaboration. There we already saw that by varying the counter reactant in an iridium processes to make different films, the one that gave the lowest growth per cycle, in fact, gave the best conformality. And that was then a bit puzzling, and we also wrote it in the paper that we don't really understand where the result comes from. But it's corresponding exactly to this trend that we simulate here. And also in a paper by Jim and Ylivaara, this is the LHAR3 paper, so to say. Here we were investigating the TMA, trimethyl aluminum water process, and in a case where we were varying the purge time, we saw that overall the growth per cycle is coming down. This tells something about the process itself. Of course, maybe there's some reversibility there to see, but when the growth per cycle was coming down, then we were growing deeper. So that's exactly also this trend. And while I know that to many it's not intuitive, when you think it through, it actually is pretty understandable. So you have the same number of molecules coming in, and if the adsorption capacity is higher, then those do not manage to get so far into the structure before they are adsorbed. It does lead to a higher total amount, but a smaller penetration depth. All right, and here is a summary where that we made about varying those different parameters one by one, and we made the variation both in free molecular flow and transition regime. Here is the penetration depth and the slope of the scale thickness profile, adsorption front, and this is actually the absolute value of the slope, so all positive values. And this is the absolute value of the adsorption front of the type 1 normalized saturation profile. And you see that here the only thing that affects this is the sticking coefficient. There's no other parameter that would give a response to this when we are in free molecular flow. But when we are in the transition regime, then there are a lot of things that matter. And this simplicity was actually elegantly used by Arts et al. In a method that I will soon come back to. So saturation profile contains kinetic information. So we already saw that the value of sticking coefficient, it really affects how the shape is. And this is an example from the Ylilammi paper where this Ylilammi's model was introduced. It's a standard diffusion reaction model, but Ylilammi made simplification to be able to calculate the partial pressure analytically, meaning that it's just one differential equation plus this analytical equation to solve. And he was able to fit TMA water results, getting a sticking coefficient of 0.0017 and a equilibrium constant for the adsorption. So this assumes also reversible reactions of 219, and this is signifying pretty much irreversible reactions. This is a high value and it corresponds to basically irreversible reactions. Titanium dioxide had a different trend. So there's a decreasing trend and then a faster decreasing trend. And with this fitting, that gave a sticking coefficient of 0.1, which is a very high value, and an equilibrium coefficient of 0.25, which then tells that actually the reversible reactions are important. So I wouldn't say that these, especially in the titanium dioxide case, these are necessarily physically very meaningful values, but the fact that we are able to fit this, it's already good. It's possible that there's some other reason also for that observed low value of equilibrium concentration, equilibrium coefficient. It could also be, for example, that there's readsorption of hydrogen chloride that is produced in this process that is responsible for that number. But in any case, this already shows that it's possible to extract kinetic information from these saturation profiles or thickness profiles. And now I get to the Arts et al. Slope method, which I already mentioned earlier. So Karsten Arts was actually really clever to notice that sticking coefficient is the only parameter that is affecting the slope where the coverage is half. And he derived this empirical formula where just by measuring the slope of the saturation profile, one can back calculate the sticking coefficient. This method does require that you are in the free molecular flow regime so that the Knudsen number is much larger than 1. Yeah, this is of course corresponding to what we then later were analyzing for the effect of those parameters. In the table I showed that this is the only response is here to observe. And yeah, here is an example from our paper also where this sticking coefficient was varied, and here we also see the similar trends in the slope versus sticking coefficient. And that's not the only thing that Karsten Arts was clever with. He also developed what I here call the penetration depth method to extract information of plasma recombination probability. Actually, this is for the neutrals from observing the penetration depth. So it's a oxygen radical recombination probability. He has gotten these values, and these are not just for ALD, they are representing the plasma properties, and they are fundamentally valuable. And these recombination probabilities, I believe that they are lower than what some were expecting. And this is really fundamental progress that's enabled by these test structures. And very recently, from the same Eindhoven group, they published another paper where they had looked at atmospheric pressure plasmas and also extracted these recombination probabilities of oxygen radicals and gotten pretty much similar values as in those earlier works, but this is now for Knudsen number roughly 1. All right, then I will move to a comparison that we made. So this is a recent paper by Järvilehto et al. And here we compared at identical conditions and at conditions which are good for both models. We compared the diffusion reaction model by Ylilammi and the ballistic transport reaction model by Yanguaskill and Elam. And this comparison work was really open science enabled because Yanguaskill published his code, MacBall code. He placed it in GitHub and let us know. And I got interested in that right away. And I actually took a summer worker to look into the code, and then next summer another one, and that's when Yanis joined. And he made this comparison, and now recently we wrote it up into a paper. So we were looking at the predictions or simulations by these models for identical conditions which are fulfilling all requirements. So Knudsen number it had to be much higher than 1 because we had that ballistic transport reaction model. It was 100 or higher for all those cases. And we made a systematic comparison. There's more in the paper, there's a little bit here, and let's just look at this panel B here. So in this case, we have varied the partial pressure of reactant and then observed how the saturation profile looks like, or actually the surface coverage in this case. Qualitatively, we see the same things. The shapes are similar. We basically see a similar constant value of surface signifying saturation in the beginning, and then the value is coming down, and when the pressure is increasing, we are going deeper. There is this one thing here at the end, though, that we see only in the ballistic transport reaction model, but not in the diffusion reaction model, and that's corresponding to growth at the end of the test structure. So the diffusion reaction model cannot analyze what happens here. It doesn't really care if there is an end or not, but this ballistic transport reaction model cares a lot, and that's where we see this growth accumulating. That's also the reason why you see here this little elephant. It's a phenomenon that's not looked very much into in the ALD literature, and it needs a name. And I would hope that we would get a systematic name in the field, and we are proposing to call it a trunk because it looks like the trunk of an elephant. And I wanted to have this here because also in our group where people easily give different names, and someone was calling it also a tail, but this is really something that it's in front of everything. It can't be a tail, but a trunk is a fine name. But then when we compare these results quantitatively, we see that for this ballistic transport reaction model, the growth is going deeper. And we also see that this slope here, it's less steep. penetration depth is less for the diffusion reaction model than for the ballistic transport reaction model, whereas slope is higher for the diffusion reaction model than the ballistic transport reaction model. So I find this very important. So far there has not been a quantitative comparison of models. There has just been a lot of modeling, or quite some modeling results, but now we see that when we do the same with two models, we don't get exactly the same results. And I would say that that's also expected. And for the question whether one of these would be right and another one wrong, well, I don't think that's the case. I think the saying is good that all models are wrong, some are useful. These are both certainly useful, and I think that this type of work should continue. Yeah, I'm in favor of open science. The funders of research, they would like us to publish everything, all of our data as open science. I think that, well, I believe more in like sustainable open science. I think that when we do things wisely, we can do things so that they are useful to us researchers. And I do think that, for example, the publishing research code, like done by Yanguaskill and also done by us, I'll go back and show. So we also have published our code. It's also available as Dream ALD in GitHub. And by the way, the Karsten Arts code is also nowadays available there. So code is one thing, but data is another thing, and it would be great if when people are measuring thickness profiles produced by these test structures, these or others, that those would be made available to other researchers to investigate. There is a real need for that. You see it, for example, from here. This is a paper by Aginski et al. From Solid State Electronics, where they have actually used our data and analyzed it with their modeling approaches. This they have just extracted from publications, but it would be much better if we would place our data directly as data points for others to use. There is in zenodo.org, there is already a community called ALD Saturation Profile Open Data, where anyone can upload their data to Zenodo and then ask to include in this community. One last piece of progress. So something that can also be done with these test structures is not just investigate ALD, but also the components that might be there, but you don't really wish to have. So unwanted CVD. And I'm not aware of any experimental studies made on this, but this review article by Kremers et al. For that, actually, Monte Carlo simulations were made to look at the continuous CVD component in addition to the ALD component and how would it look like. And this is how it was then found to look like, that in the beginning of the growth, you are not getting that saturation, but you have this continuous component here. And so that would be for the reactant self-decomposition, but then another thing is also the mixing of the reactants in the gas phase, and that I don't know that anyone would have done, simulated or measured yet. All right, outlook, what's next? Well, these microscopic lateral high aspect ratio test structures, they really have opened up a new parameter space for scientific exploration. And there's a lot of scientific work, very basic scientific work that can be done. Measurement of experimental saturation profiles for different ALD processes. There are surely more than 700 published of ALD processes, and there are these thickness profiles are available to only a few. There would be a lot of work to do there. In addition to measuring those, modeling also. For example, the surface chemistry assumed in the models, it's always that single side Langmuir adsorption. There would be space for a little bit more complicated things, and also extracting kinetic parameters from there, either by the Arts et al. Model or by other means, especially if you are not in that free molecular flow regime. Yeah, I'm really thinking that this open science can lead to more effective science and global collaboration, and that zenodo.org is already available as a database. I see that open science a little bit as this train of elephants, that it has been a little bit difficult and taken a lot of time to get started, but once someone is leading and showing the way, then it's easy to follow. So I would give credit to Angel Jangoskil, who has been the first one to publish this research code to GitHub, and it's been easier for us to follow. And the same with Zenodo and open data. I hope that the examples help. And yeah, as a reminder that there are these figures available in Wikimedia Commons with a Creative Commons license. Acknowledgements. I would like to thank all collaborators throughout the years. I've tried to name them in the slides. And the funding has been provided, as said, by Academy of Finland and Tekes, VTT, Business Finland, and now also Research Council of Finland. And here you see my group as it was in May. And also I'd like to thank Chipmetrics. And thank you for your attention. And here is a list of extra materials in the slide set.